November 12, 1942. Richmond, California, 11:29 in the morning. Clay Bedford checked his pocket watch one last time as the massive hull began its slide toward San Francisco Bay. 4 days, 15 hours, and 29 minutes. That's how long it had taken to build an entire cargo ship from keel to launch a vessel 441 feet long, weighing 10,500 tons, assembled from 250,000 individual parts. The SS Robert E. Peary hit the water amid cheers from the assembled crowd. But Bedford wasn't celebrating yet. The ship still needed 10 more days of fitting out before she could steam to war. What mattered was the principle the Peary had just proven. German U-boats were sending Allied merchant ships to the bottom of the Atlantic faster than anyone thought possible. Admiral Karl Dönitz's submarines had sunk over 868 ships in 1942 alone, 3 million tons of Allied shipping erased in a single year. The mathematics of defeat were being written in the cold waters of the North Atlantic. To strangle Britain, Germany needed to sink 300,000 gross tons of merchant shipping each month, and for most of 1942, they were exceeding that target. Every supply convoy that crossed the Atlantic was a gamble. Every cargo ship represented months of traditional shipyard labor. By every rational calculation, the Allies were losing the tonnage war. What Dönitz didn't know, couldn't have known, watching his U-boat commanders tally their victories, was that an obscure industrial engineer named Henry Kaiser had just made his entire strategy obsolete. Not through superior weapons or better tactics, but through something far more dangerous to German war plans. Kaiser had figured out how to build cargo ships faster than submarines could sink them. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Liberty ship program would become the industrial equivalent of a tidal wave. Between 1941 and 1945, American shipyards would produce 2,710 Liberty ships, the largest class of ships ever built to a single design. At peak production in 1943, 3 new Liberty ships were being launched every single day. The ships themselves were nothing special. President Franklin Roosevelt himself called them dreadful-looking objects. The press nicknamed them ugly ducklings. They were slow, utilitarian, and built to last maybe 5 years before being scrapped. But they didn't need to be beautiful. They needed to float, carry cargo, and get built fast enough to bury the Kriegsmarine in an avalanche of steel. What made this achievement extraordinary wasn't the ships themselves, it was how they were built. Kaiser and his competitors had done something that every naval power on Earth insisted was impossible. They had turned ship production into a manufacturing process, assembly line construction for vessels that traditional shipyards said required 6 months of skilled craftsman labor. The story begins not in a shipyard, but in the deserts and mountains of the American West, where a man who had never built a ship in his life was learning lessons that would reshape industrial warfare. May 9, 1882. Sprout Brook, New York. Heinrich Kaiser was born to German immigrants barely a decade after they'd arrived in America. His father Frank had been a shoemaker in Germany before crossing the Atlantic. His mother Mary had been a nurse. The family was poor. By 1899, they'd moved to Whitesboro, New York, near the Erie Canal. Young Henry, he'd Americanized his name by his teenage years, left school at 13 to work. He got a job at a dry goods store, then as an apprentice photographer. He worked, watched, learned. He developed a reputation for relentless energy and an unusual skill for organizing complicated projects. But he had no formal engineering education, no college degree, nothing to suggest he'd eventually command 250,000 workers building instruments of war. In 1906, at age 24, Kaiser moved west. He got a job with a hardware company in Spokane, Washington, selling construction supplies. Within years, he'd saved enough to start his own paving company. He began with small road projects, learning the business from the ground up. What set Kaiser apart wasn't technical genius, it was his ability to see construction projects as systems that could be optimized. In 1914, he founded Henry J. Kaiser Company. His first innovation was using heavy construction machinery where others relied on manual labor. Machines were faster, more reliable, and once you'd invested in them, cheaper than hiring crews of workers. He won contracts for road construction throughout the Pacific Northwest, building his reputation as a contractor who delivered on time and under budget. Then came Cuba. In 1927, Kaiser took on a massive subcontract to build 200 miles of road and about 500 bridges across the length of Cuba. The contract was worth almost $20 million more than everything Kaiser had done since starting his business. It was a disaster waiting to happen. The heat was crushing. His American machinery kept breaking down in the tropical conditions. Suppliers cheated him. Cuban officials demanded bribes. Kaiser learned 2 lessons in Cuba that would define his career. First, when machines failed, people succeeded. His Cuban workers, doing the work manually while the machinery was repaired, finished tasks faster and better than the broken equipment ever had. People, properly organized and motivated, were the most important resource. Second, he learned the value of vertical integration, paying inflated prices to suppliers, watching shipments arrive late or not at all. Kaiser realized he needed to control his own supply chains. If he couldn't trust others to deliver what he needed when he needed it, he'd manufacture it himself. The team finished the Cuban project 3 years ahead of schedule in 1930. Kaiser returned to the United States with a transformed understanding of large-scale construction. Then came the dams. In 1931, Kaiser joined 6 other major construction companies to form a consortium called simply the 6 Companies. Their target was the most ambitious construction project in American history, the Hoover Dam on the Colorado River. The bid was $48.9 million, about $600 million in today's money. The dam would require more concrete than all previous dams built by the Federal Bureau of Reclamation combined. The Colorado River had to be temporarily rerouted through tunnels blasted into canyon walls. The work had to be done in the Nevada desert without existing infrastructure. Temperature in the summer exceeded 120 degrees Fahrenheit. Winter brought freezing temperatures, and the timeline was impossibly tight, 7 years to complete what traditional estimates said would take 10. Kaiser was assigned to be the project's liaison in Washington. While his partners managed the physical construction, Kaiser learned the corridors of power. He studied which officials had authority to approve changes, which congressmen controlled appropriations, which bureaucrats could expedite permits. He developed relationships with politicians and administrators who would remember him when future contracts were awarded. The Hoover Dam was completed in 1936, 2 years ahead of schedule. It was an engineering marvel and a financial success. More importantly for Kaiser, it established him as a major figure in American heavy industry. After Hoover came the Bonneville Dam, then Grand Coulee each, project teaching Kaiser new lessons about managing massive construction efforts. At Grand Coulee, Kaiser encountered Dr. Sidney Garfield, a young physician who developed an innovative healthcare plan. Instead of workers paying for medical care when they got sick, Garfield proposed they prepay a small weekly cost. The workers received preventive care and treatment for injuries and illnesses without additional charges. This kept them healthier and on the job longer. Kaiser implemented the plan at Grand Coulee. It worked brilliantly. Workers caught medical issues early. They missed fewer days due to illness. The upfront investment in healthcare paid for itself through increased productivity. Kaiser filed this lesson away, taking care of your workforce not out of charity, but because healthy workers were more productive was sound business. By 1939, Kaiser had become wealthy building dams, roads, and bridges. He'd mastered large-scale project management, learned to navigate Washington bureaucracy, and developed a network of skilled contractors and engineers who trusted his leadership. He was 57 years old. Most men would have considered retiring or at least slowing down. Kaiser saw an opportunity. Europe had descended into war. Germany's conquest of Poland in September 1939 had demonstrated the power of mechanized warfare. France would fall in June 1940, collapsing in 6 weeks under the weight of German panzers and Luftwaffe bombers. Britain stood alone, an island nation dependent on merchant shipping to survive. And Britain's merchant fleet was being systematically destroyed. German U-boats operating from French Atlantic ports could reach far into the Atlantic. The submarines hunted in wolf packs, coordinated groups that overwhelmed convoy escorts. In 1940, Germany sank nearly 1,000 Allied merchant ships. In 1941, the toll reached 875 ships. The mathematics were brutal. Britain needed to import food, fuel, raw materials, and weapons. Every commodity arrived by sea. If the Germans could sink ships faster than they could be replaced, Britain would starve into surrender without Germany ever needing to invade. The British government, desperate for merchant shipping, turned to American shipyards for help. In December 1940, Britain ordered 60 emergency cargo ships from American yards. The design was based on a British freighter called the Dorrington Court, a simple, reliable vessel built to 19th century specifications. It wasn't fast or sophisticated, but it could carry cargo and didn't require advanced technology to construct. The U.S. Maritime Commission modified the British design to conform with American construction practices. They designated it EC2SC1, EC for emergency cargo, 2 for a ship between 400 and 450 feet long, S for steam engine, C1 for the design type. The ships would eventually be called Liberty ships, but in December 1940, they were simply an emergency measure to help Britain survive. The Maritime Commission needed shipyards to build these vessels. Traditional shipyards on the East Coast were already committed to naval vessel construction. The Commission looked west, to yards that could be built from scratch, where labour was available, and where contractors might try unconventional approaches. Henry Kaiser saw the opportunity and proposed something radical. He'd never built a ship. His company had no shipbuilding experience whatsoever. His background was dams, roads, cement, and construction machinery. But Kaiser looked at the specifications for the EC2 cargo ship and saw something everyone else was missing. It was just a complicated assembly project. A dam was thousands of tons of concrete shaped into a specific form. A road was layers of gravel, aggregate, and pavement organized in sequence. A ship was steel plates, engines, and equipment organized into a floating structure. The specifics were different, but the principles were identical. You needed a design, materials, workers trained for specific tasks, and a system that moved the work through production stages efficiently. Kaiser partnered with Todd Shipyards, an established shipbuilding company, and Bath Iron Works. Todd and Bath brought shipbuilding knowledge. Kaiser brought revolutionary insights about industrial production and a willingness to ignore every tradition that didn't serve the goal of building ships faster. In December 1940, construction began on Kaiser's first shipyard in Richmond, California. Simultaneously, work started on another yard in South Portland, Maine. These weren't traditional shipyards. They were designed from scratch around the principle of assembly line production. Kaiser studied how Henry Ford built automobiles at the River Rouge complex in Detroit. Cars were assembled from thousands of components manufactured separately, brought together on moving assembly lines where specialized workers performed specific tasks repeatedly. Could ships be built the same way? Traditional shipbuilders said absolutely not. Ships were custom constructions. Every vessel was unique. Skilled craftsmen built them from the keel up, fitting components by hand, adjusting for tolerance variations. Each worker needed to understand the entire ship, not just one task. This craftsmanship took years to develop. You couldn't just hire unskilled workers off the street and teach them to build ships. Kaiser believed they were wrong. Not about the difficulty, they were right that ship construction was complex. They were wrong about the solution. The complexity itself created opportunity. If you designed a ship specifically for mass production, if you standardized every component, if you trained workers for specialized tasks instead of expecting them to master everything, you could achieve production rates that traditional methods couldn't match. The key was prefabrication. Instead of building the ship entirely on the slipway where it would be launched, you built major sections, double bottom units, bulkheads, deck houses, stern assemblies, and bow sections in separate areas of the yard. These sections, some weighing up to 45 tons, could be fabricated simultaneously by different work crews. When the sections were complete, cranes would lift them onto the ship's growing hull, where they'd be welded into place. This approach meant that 80% of the ship was already assembled before the keel was laid. The slipway, always the bottleneck in traditional construction, was occupied for a fraction of the normal time. Multiple ships could move through production simultaneously, rather than tying up the slipway for months. Then came welding. Traditional ships were riveted. Steel plates overlapped, holes were drilled through both layers, and red-hot rivets were driven through the holes and hammered closed. Riveting was skilled work requiring 2 or 3 workers per rivet, one to heat it, one to hold it in place, one to hammer. A Liberty ship built with rivets required millions of them. Welding was faster, lighter, and far easier to teach. 2 steel plates butted together. A welder ran a torch along the seam, melting steel from a welding rod into the joint, fusing the plates. One worker could do what had required a riveting crew. The joints were stronger properly done, a weld was stronger than the base metal. And welding saved weight. No overlapping plates meant less steel. The welded seam added minimal weight compared to rows of heavy rivets. There was resistance. Naval architects worried about welding. The joints were untested. Welds could fail catastrophically if done improperly. The heat from welding might create stress points where cracks could form. Riveted construction had centuries of proven track record. Switching to welding for emergency production seemed reckless. Kaiser's response was pragmatic. Welding was faster, and speed mattered more than perfection. These ships were designed as emergency vessels expected to last 5 years. If welding saved months of construction time, the strategic advantage outweighed the technical risks. And welding had another crucial advantage: it could be taught to inexperienced workers in weeks, not years. Women could weld. Men who'd never worked with metal could weld. Former farm workers, shop clerks, teachers, housewives, anyone with steady hands and attention to detail could learn to run a welding torch. Kaiser recruited workers from across the United States. He advertised in newspapers, sent recruiters to rural areas with high unemployment, and hired without discrimination. His shipyards employed thousands of African Americans at a time when most industries excluded them. He hired women in unprecedented numbers, about 10% of the workforce. He built housing for workers, established childcare facilities, and implemented Dr. Garfield's prepaid healthcare program. By mid-1941, the Richmond shipyard was operational. The first British freighter ordered under the original 60-ship contract, the SS Ocean Vanguard, was launched in August 1941. It had taken traditional shipbuilding methods, but Kaiser's team was learning. The second ship went faster, the third faster still. Then came September 27, 1941, Liberty Fleet Day. 14 EC-2 ships were launched simultaneously from yards around the country. President Roosevelt attended the launch of the first one, the SS Patrick Henry, at the Bethlehem Fairfield Shipyard in Baltimore. In his speech, Roosevelt invoked Patrick Henry's Revolutionary War Declaration, "Give me liberty or give me death," saying these new cargo ships would bring liberty to Europe. The name stuck: Liberty ships. The SS Patrick Henry had taken 244 days to build, about 8 months. It was faster than traditional construction, but still agonizingly slow compared to what would be needed. German U-boats were sinking ships in days. Building replacements took months. The mathematics didn't work, but September 27, 1941 was just the beginning. Kaiser and his engineers were refining their processes with every ship. They identified bottlenecks, redesigned workflows, improved training programs, optimized the movement of materials through the yard. The learning curve was steep, but the improvements were dramatic. By January 1942, average construction time had dropped to 197 days, about 6.5 months. In June 1942, the average was down to 120 days, 4 months. The ships were coming faster, but Germany's U-boats were reaching peak efficiency. June 1942 marked the peak of Germany's success in the Battle of the Atlantic. That month, U-boats sank 124 Allied merchant ships over 800,000 tons. The losses were catastrophic. Oil tankers exploded off the American East Coast within sight of shore. Convoy escorts proved inadequate against wolf-pack tactics. Merchant sailors died by the thousands, burned alive in flaming oil slicks, or frozen to death in lifeboats that rescue vessels never found. If the production rate couldn't be accelerated dramatically, Britain would be starved into submission before American military power could be brought to bear. Kaiser knew it. The Maritime Commission knew it. Roosevelt knew it. The challenge was clear. Ship production had to exceed losses, not by a small margin, but by such an overwhelming margin that Germany couldn't possibly keep pace. Not just replace losses, bury the enemy in ships, build so many vessels that sinking them became pointless. September 1942, Oregon Shipbuilding Corporation, Portland. The yard manager called a meeting of foremen and announced a challenge. The Richmond yards had been cutting production time aggressively. Portland needed to prove they could do better. The target was set 10 days from keel laying to launch for a single Liberty ship, not average production time across multiple vessels, but one ship built start to finish in 10 days. It seemed impossible. Even with prefabrication and welding, 10 days meant completing work that normally took 6 weeks. Every section would need to be ready precisely when needed. Every welder, every crane operator, every assembly crew would need to function with perfect coordination. One delay would cascade through the entire schedule. The ship was designated the SS Joseph N. Teal. Keel laying began on September 13, 1942. For the next 10 days, the Portland yard operated around the clock. Prefabricated sections arrived from assembly shops on railroad flat cars. Cranes lifted 40-ton bulkheads into position. Welders worked in shifts, their torches glowing like fireflies across the growing hull. The sound of metal on metal, the hiss of cutting torches, the rumble of cranes, it never stopped. September 23rd, 10 days after the keel was laid, the Joseph N. Teal slid into the Willamette River. The yard had done it, 10 days from start to launch. Word spread through the shipbuilding industry like wildfire. If Portland could do it in 10 days, what was possible with even more optimization? Henry Kaiser was asked by a reporter if it could have been done faster. Kaiser, never one to back down from a challenge, said it probably could. His Richmond Yard No. 2 had been refining prefabrication techniques even beyond what Portland had achieved. Components were being manufactured in specialized shops throughout Northern California and transported to Richmond for final assembly. What if every possible section was prefabricated? What if the yard coordinated the timing perfectly? What if they mobilized every available resource for a single ship? Kaiser decided to find out. The ship would be the SS Robert E. Peary, named after the Arctic explorer. The goal wasn't practical production. Nobody could sustain the resource commitment required. The goal was propaganda. Show the world, show Germany, show America's own workforce what American industrial capacity could achieve when fully mobilized. Prove that U-boats couldn't sink ships faster than America could build them. November 8, 1942. Richmond Shipyard, No. 2. Midnight. Under floodlights that turned night into artificial day, workers laid the keel plates for the Robert E. Peary. The clock started ticking. Every section of the ship had been prefabricated during the previous weeks. Double-bottom units sat on railroad cars, waiting. Bulkheads were staged near the slipway. The bow section, a massive assembly of steel plates welded into the distinctive curved form, was ready to be lifted. The stern frame assembly, complete with mounting points for the rudder and propeller shaft, was positioned. The engine, a 140-ton vertical triple expansion steam engine, had been assembled and tested in a separate facility. It wasn't an advanced engine. Triple expansion engines were obsolete technology by 1942. Steam turbines were far more efficient, but steam turbines required precision manufacturing for their complex reduction gears. Only a few companies could manufacture them, and they were committed to building turbines for destroyers and cruisers. The Liberty ship engine was deliberately simple, 3 cylinders of different sizes, arranged vertically. Steam entered the smallest high-pressure cylinder, expanded and moved to the medium-pressure cylinder, expanded again and moved to the large low-pressure cylinder, then exhausted to the condenser. The engine had been designed in the late 19th century and changed little since. It was rugged, reliable, and most importantly, 18 different companies could manufacture it. Parts from one manufacturer's engine were interchangeable with parts from another. Any merchant seaman who'd spent time in an engine room knew how to operate and maintain it. Simplicity was a strategic choice. Complex systems required skilled operators. Simple systems could be maintained by sailors with basic training. Ships would be crewed by merchant mariners, many of them new to maritime service. The engine had to be foolproof. The construction of the Peary proceeded with mechanical precision. Hour 1, the keel plates were laid and welded into a continuous spine. Hour 6, the first bottom shell plates were erected and welded to the keel. Hour 12, the double bottom sections, massive assemblies that formed the ship's bottom and contained fuel and water tanks, were lifted by crane and set in place. Day 2. The hull was taking shape. Welders worked in teams, running continuous beads along seams that stretched the length of the ship. Bulkheads, the internal walls that divided the ship into compartments, were lifted into position and welded to the deck plates. Each bulkhead added structural strength and watertight integrity. If the hull was holed by torpedo or collision, the bulkheads would limit flooding to a single compartment. Day 3. The deck plates were going on. Deck houses, the structures that would contain the crew quarters, galley, and navigation bridge, were lifted aboard as complete units. These prefabricated sections had windows already installed, interior walls already constructed, even some electrical wiring and plumbing already in place. Setting them on deck and welding them down took hours instead of weeks. Day 4. The engine was lowered into the engine room. The massive assembly descended on cables, guided by workers who signaled the crane operator with hand gestures. When it settled onto its mounting bed, workers immediately began bolting it down and connecting the shaft to the propeller. The boilers, 2 of them, capable of generating the steam, the pressure needed to drive the engine, were lowered into the boiler room. Throughout the construction, Bedford, the yard manager, monitored progress with a stopwatch. Any delay was immediately addressed. If a welding crew fell behind schedule, additional welders were pulled from other projects. If a crane developed mechanical issues, backup cranes were standing by. Nothing was allowed to slow the pace. By November 11th, 3 days and 15 hours after the keel was laid, the Peary was recognizably a ship. The hull was complete, the superstructure was in place, the engine and boilers were installed. Electrical systems were being connected, fuel tanks were being tested for leaks. The ship still needed masts, rigging, lifeboats, armament, and dozens of other details before she'd be ready to sail, but she was ready to launch. November 12, 1942, 11:29 in the morning. 4 days, 15 hours, and 29 minutes after the keel was laid, the Robert E. Peary slid down the ways into San Francisco Bay. Newsreel cameras recorded the moment. Reporters from across the country attended. The launch made headlines from Seattle to Oklahoma City to Boston, but officials at the Permanente Corporation were careful to clarify what the record meant. "We are not primarily trying to break records," Bedford told the United Press Association. "Our main purpose has been experimenting in new prefabrication methods, and, after receiving hundreds of valuable suggestions and time-saving inventions from our workers, we decided to try them all on one hull and see what would happen." The Peary wasn't an example of sustainable production. The resources committed to building one ship in 4.5 days couldn't be maintained across an entire shipyard. But the exercise proved what was theoretically possible. It demonstrated that with perfect coordination, unlimited resources, and optimal prefabrication, ship construction could be compressed into days rather than months. More importantly, it provided a massive morale boost for workers throughout the Kaiser yards. If the Peary could be built in 4.5 days, then 40-day production schedules weren't asking too much. The record showed workers what they were capable of achieving. The Peary needed 10 more days of fitting out before being delivered to the Maritime Commission. Masts were stepped, cargo booms were installed, 5-inch deck guns and 20mm anti-aircraft guns were mounted. Lifeboats were hung from davits. The final coat of grey paint was applied. November 22, 1942. The SS Robert E. Peary departed San Francisco Bay with a crew of 43 merchant mariners and 17 U.S. naval armed guards who would operate the defensive weapons. Her first destination was New Caledonia in the South Pacific, carrying food and war supplies. The Peary would serve throughout the war, making voyages to the Pacific, the Atlantic, and the Caribbean. In 1944, she would transport troops and equipment to Normandy, making supply runs during the D-Day invasion under constant attack. She would survive the war intact and continue service until 1963, when she was finally scrapped in Baltimore. 21 years of service for a ship designed to last 5. But in November 1942, the Peary's significance wasn't her individual service. It was what her construction proved about American industrial capacity. Germany's intelligence services, monitoring American production, reported the 4.5-day ship as propaganda. Impossible to believe. German naval architects insisted the reports had to be exaggerated. Ships couldn't be built that fast. The Americans must be counting only certain phases of construction, not the actual full build time. They were wrong. The Peary's construction time was real, and while that specific pace couldn't be sustained, it demonstrated that American industry had fundamentally transformed shipbuilding from a craft into a manufacturing process. By early 1943, average Liberty ship construction time across all yards had dropped to 42 days. The bottleneck was no longer construction time, it was the availability of steel, which Kaiser addressed by building his own steel mill at Fontana, California. By 1943, Kaiser yards were producing ships faster than the Maritime Commission could find crews for them. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The transformation in shipbuilding capacity was staggering. In 1941, American shipyards had delivered 863 merchant ships of all types. In 1942, the number reached 1,549 ships. But 1943 saw the full flowering of the emergency program. That year, American shipyards launched 19 million tons of merchant shipping, more than 3,000 ships of various types, including over 1,500 Liberty ships alone. At peak production in 1943, American shipyards were launching 3 Liberty ships every single day. Kaiser's 7 yards were producing 50 ships per day across all vessel types. The Oregon Shipbuilding yard maintained an average pace of 17 days per Liberty ship for months, building multiple vessels simultaneously on different slipways. The workforce transformation paralleled the production miracle. In 1939, American shipyards employed about 50,000 workers. By 1943, employment had reached 1.5 million workers, an increase of nearly 1,400%. Most of these workers had never built a ship before. Many had never worked in heavy industry at all. Josie Lucille Owens had been a waitress in Richmond before the war. In 1943, she was photographed welding hull plates on the SS George Washington Carver. The photograph, showing a young African-American woman in welding leathers, her torch glowing as she worked, became iconic. Rosie the Riveter imagery came from shipyard workers like Owens' women performing industrial work traditionally reserved for men. The Kaiser yards employed approximately 50% women and African-American workers in some facilities. This wasn't altruism. Kaiser needed workers desperately, and he hired whoever could do the job regardless of race or gender. The prepaid healthcare program, the childcare facilities, the training schools all served the practical purpose of keeping workers healthy, supported, and productive. Training was systematic. New workers spent 2 weeks learning their specific task before touching actual ship components. A welder learned to run consistent beads on training materials before being assigned to hull plates. A crane operator practiced on training rigs before lifting 40-ton sections over working crews. The training was narrow, workers learned specific operations, not general shipbuilding, but that specificity meant they could become proficient quickly. The system embodied division of labor taken to its logical extreme. No individual worker understood how to build a complete ship, but each worker became expert at their assigned task. When thousands of specialized workers performed their tasks in coordinated sequence, ships emerged from the organized chaos. The prefabrication shops were marvels of logistics. A double-bottom section required hundreds of individual steel plates cut to precise specifications, welded together to form tanks and structural ribs, tested for watertight integrity, then transported to the main shipyard for installation. Managing the flow of materials, ensuring that the right section arrived at the right slipway at precisely the right moment required planning that rivaled military operations. Kaiser established a tracking system that monitored every major component. Prefabricated sections were tagged with destination information. Railroad flat cars moved through the yard on schedules coordinated to the hour. If a crane was scheduled to lift a bulkhead at 2 o'clock Tuesday afternoon, the flat car carrying that bulkhead would arrive at 1:45. The precision was remarkable, given that this was decades before computers or digital inventory management. The welding revolution extended beyond speed. Properly executed welds produced joints stronger than riveted connections, but welding introduced problems that wouldn't become apparent until ships were in service. Some Liberty ships developed cracks in cold water. A few suffered catastrophic hull failures. The T-2 tanker Schenectady broke completely in half while docked in calm water in January 1943, before making her first voyage. The problem was brittle fracture. Welding created continuous joints where stress could propagate. In riveted construction, a crack reaching a rivet hole would stop. The hole acted as a stress relief point. In welded construction, a crack could run the entire length of a seam. Cold temperatures made the steel brittle, more susceptible to cracking. Design choices like square hatch corners created stress concentration points where cracks could initiate. The solution required metallurgical changes and design modifications, higher quality steel with better fracture toughness, rounded corners instead of square ones, crack arrestor plates welded across seams to stop crack propagation, better welding techniques and more rigorous quality control. These modifications were implemented progressively throughout 1943 and 44. Kaiser's reputation suffered from the cracking problems. Competitors who'd opposed his methods pointed to the structural failures as proof that traditional riveted construction was superior, but the Maritime Commission defended the KTR welding approach. Even with the cracking issues, welded ships could be built far faster, and speed was the strategic priority. The modifications largely solved the problems, and welded construction became standard for modern shipbuilding. The impact on the Battle of the Atlantic became apparent during 1943. In the first quarter of the year, German U-boats maintained their effectiveness, sinking Allied merchant ships at rates that seemed to justify Dönitz's confidence. But American shipyards were now producing ships faster than they could be sunk. In March 1943, U-boats sank about 100 Allied merchant ships. American yards alone launched 150 ships that month. April saw similar numbers, but May 1943 marked the decisive turning point. That month, designated Black May by German submariners, the U-boats suffered catastrophic losses. 41 U-boats were destroyed in May 1943, a quarter of Germany's operational submarine force lost in 31 days. The casualties were unsustainable. Allied convoy escorts had become more effective, equipped with improved radar and depth charges. Long-range patrol aircraft closed the air gap in the mid-Atlantic where U-boats had previously operated with relative safety. But the most devastating factor was simpler than technology. The U-boats couldn't sink ships fast enough to matter anymore. In May 1943, U-boats sank 58 Allied merchant ships, totaling about 300,000 tons. American shipyards launched over 400 ships that month, totaling more than 2 million tons. For every ship the U-boats sent to the bottom, 8 new ones entered service. The mathematics that had threatened Britain's survival in 1942 now threatened Germany's strategic position. Admiral Dönitz realized his submarine campaign was failing. On May 24, 1943, he ordered a temporary withdrawal of U-boats from the North Atlantic. The submarines retreated to less dangerous waters, never to regain their earlier effectiveness. The Battle of the Atlantic continued until Germany's surrender in May 1945, but after May 1943, the outcome was inevitable. Germany built approximately 1,000 U-boats during the war. They sank 3,500 Allied merchant ships totaling 14.5 million tons. In exchange, 783 U-boats were destroyed, and 30,000 German submariners died, 3/4 of the entire U-boat force. But here's the extraordinary statistic. During the war, American shipyards produced approximately 5,600 ships commissioned by the Maritime Commission, plus additional vessels for private companies and foreign governments. Total American wartime maritime production exceeded 55 million tons of shipping. The Liberty ship program alone, 2,710 ships, represented over 29 million tons. Germany's entire submarine campaign, conducted at enormous cost in lives and resources, reduced Allied shipping capacity by about 14 million tons. American production added 55 million tons. The net result was that Allied shipping capacity increased by over 40 million tons during a war where Germany's entire strategy depended on reducing it. This wasn't a close-run thing. It wasn't a narrow Allied victory snatched from the jaws of defeat. It was an industrial avalanche that buried the Kriegsmarine in ships they couldn't possibly sink fast enough. The Liberty ship program, combined with escort carriers, improved convoy tactics, and better anti-submarine weapons, didn't just defeat the U-boat threat. It made the entire concept of tonnage warfare obsolete. The transformation proved several principles that reshaped modern warfare. First, that production capacity could be a weapon as devastating as any fielded on the battlefield. Second, that industrial processes developed for civilian goods could be adapted to military equipment. Third, that speed of production mattered more than perfection of individual units. And fourth, that properly organized and trained civilian workers could perform complex industrial tasks previously thought to require years of specialized training. Henry Kaiser became a national hero. Magazines profiled him as the Miracle Man and America's #1 industrial hero. In a public opinion poll conducted near war's end in spring 1945, Americans named Kaiser as the civilian who had done the most to help win the war. President Roosevelt considered naming him as a vice presidential running mate in 1944, but Kaiser's contribution extended beyond ships. His yards also built 50 escort carriers for the Navy, small aircraft carriers built on merchant ship hulls, nicknamed baby flat-tops. These escort carriers provided air cover for convoys, dramatically increasing the vulnerability of U-boats. They hunted submarines with aircraft equipped with depth charges and radar. The combination of overwhelming numbers of cargo ships plus air cover from escort carriers made convoy attacks suicidal for U-boats. Kaiser's enterprises employed 250,000 workers across all his facilities by war's end. His cement plant at Permanente supplied concrete for Pacific military bases. His steel mill at Fontana produced steel for shipbuilding. His aluminum plant produced material for aircraft. The vertically integrated empire he'd built allowed rapid response to supply chain problems. If steel shipments were delayed, Kaiser's own mill could increase production. If cement was scarce, his Permanente plant could ramp up output. The scale of coordination required to manage this industrial empire was staggering. Moving raw materials from mines to processing plants to manufacturing facilities to shipyards required transportation infrastructure, logistics planning, and communication systems that operated continuously. Kaiser established traffic control systems that rival modern supply chain management. Railroad cars moved on schedules coordinated across multiple states. Truck convoys delivered components on timetables measured in hours. Ships carried finished vessels from Pacific shipyards through the Panama Canal to Atlantic ports for final provisioning before sailing to war. Part 3 of the Liberty ship script, Final. The human stories behind the statistics reveal what the industrial transformation meant at the individual level. Consider the trajectory of someone like Eastine Cowner, photographed in 1943 working as a scaler on the Liberty ship SS George Washington Carver. Before the war, she'd been a waitress, scaling, removing rust, mill scale, and imperfections from steel plates before welding was hard physical labor requiring endurance and attention to detail. But it paid far better than waiting tables, and more importantly, it was contributing directly to winning the war. For African Americans like Cowner, the shipyards represented unprecedented economic opportunity. Kaiser's hiring practices, driven by labor needs rather than social activism, created pathways to skilled industrial work that had been largely closed before. The yards weren't perfectly integrated. Discrimination persisted in various forms, but the sheer scale of hiring and the urgent need for workers forced a partial breakdown of traditional barriers. Women faced similar dynamics. About 10% of Kaiser's workforce was female by 1943, performing every task from welding to crane operation to electrical work. These weren't auxiliary roles or light-duty positions. Women worked in conditions as difficult and dangerous as men. They ran cutting torches that produced temperatures of 6,000 degrees. They climbed scaffolding 50 feet above the ground to weld overhead seams. They operated cranes, lifting sections weighing tons. The famous Rosie the Riveter imagery came directly from shipyard workers. The poster showing a woman in work clothes flexing her arm with the caption, "We can do it," was based on photographs of real shipyard employees. The cultural impact extended beyond the war years. Women who'd proven they could perform industrial labor successfully weren't willing to simply return to pre-war gender roles. The shipyards became one catalyst for broader social changes, but the work was dangerous. Shipyards were industrial accident zones. Welding produced toxic fumes. Cutting torches created sparks that could ignite clothing or materials. Cranes moving massive loads could crush workers if cables failed or operators misjudged distances. Falls from scaffolding caused injuries and deaths. Heat in summer and cold in winter made the work physically punishing. Kaiser's healthcare program, administered by Dr. Sidney Garfield, addressed these dangers systematically. First aid stations at the shipyards treated minor injuries immediately. The Permanente Field Hospital in Richmond handled more serious cases. The main Permanente Hospital in Oakland treated the most critical injuries. The three-tier system meant workers received appropriate medical care quickly, minimizing time away from work and improving outcomes. The healthcare model was revolutionary for its time. Instead of workers paying out of pocket for medical care, which meant many delayed treatment until conditions became serious, they prepaid a small weekly amount. In exchange, they received comprehensive care, including preventive services, vaccinations, and health education. By August 1944, 92% of Richmond shipyard employees had joined Kaiser Permanente. This wasn't charity. It was systematic investment in workforce productivity. Healthy workers missed fewer days. Early treatment prevented minor issues from becoming serious. The upfront cost of the healthcare program was offset by increased productivity and reduced turnover. After the war, Kaiser Permanente expanded to serve workers' families and eventually became one of America's largest healthcare organizations. The model proved that prepaid healthcare could work at scale. The Liberty ships themselves served in every theater of the war. They carried tanks and ammunition to North Africa for Operation Torch. They transported troops and supplies to Italy for the invasion of Sicily. They formed the backbone of the massive logistics effort supporting D-Day, the invasion of Normandy on June 6, 1944. On D-Day, Liberty ships anchored off the Normandy beaches, serving as floating supply depots. Small landing craft shuttled between the Liberty ships and the shore, bringing ammunition, food, fuel, and equipment to the armies fighting inland. German artillery targeted the ships continuously. Several were hit and damaged, some caught fire, but they kept unloading, kept supplying the invasion force, kept the logistics pipeline flowing. The SS Robert E. Peary, the ship built in 4.5 days, was there. On June 7, 1944, she transported men and equipment to Omaha Beach under constant German attack. She returned to England, loaded more supplies, and went back to Normandy on June 13. For months, she shuttled between English ports and the invasion beaches, one ship among hundreds supporting the largest amphibious operation in history. In the Pacific, Liberty ships supported the island-hopping campaign that pushed Japan back toward its home islands. They carried troops to Guadalcanal, Tarawa, Saipan, Iwo Jima, Okinawa. They supplied the bases being built on captured islands. They transported the fuel, ammunition, and food that kept the Pacific Fleet operating thousands of miles from American ports. The ships weren't glamorous. They were slow, making maybe 11 knots at top speed. They rolled heavily in rough seas, making sailors miserable. They were noisy. The triple expansion engines created a distinctive rhythmic thumping that could be heard for miles. They leaked. The welded seams sometimes dripped, especially around hatches. Crews complained constantly about the ship's shortcomings. But they worked. They carried cargo reliably across every ocean. They survived torpedo attacks. The compartmentalized construction meant a single torpedo hit usually didn't sink them. They survived storms that would have destroyed less robustly built vessels. And most importantly, there were so many of them that losing individual ships didn't significantly impact operations. About 200 Liberty ships were lost during the war, sunk by torpedoes, mines, bombs, or storms. That represented roughly 7% of the total built. Traditional naval thinking would have considered those losses catastrophic, but in the context of production that exceeded 2,700 ships, losing 200 was strategically acceptable. For every Liberty ship lost, more than 10 more were built. This calculation, accepting losses because replacement production exceeded attrition, represented a profound shift in military logistics. Historically, ships were precious assets, individually important, carefully protected. The Liberty program treated ships as expendable resources, valuable not individually but in aggregate. This was industrial warfare reduced to its essence. Victory went to the side that could produce faster than the enemy could destroy. Germany never adapted its strategy to counter this approach. U-boat construction continued throughout the war, with increasingly sophisticated submarines being developed. The Type XXI U-boat, introduced in late 1944, was technologically superior to anything the Allies fielded faster underwater, quieter, equipped with better torpedoes. But it came too late and in too few numbers. Germany launched 47 Type XXI boats before the war ended. Only 2 conducted war patrols, and neither sank any ships. The comparison illuminates the strategic blindness. Germany invested enormous resources developing advanced submarines. The Type XXI represented cutting-edge naval engineering, but technological sophistication couldn't overcome numerical reality. Even if every Type XXI submarine had sunk 10 Allied ships, an impossible achievement, they would have destroyed fewer than 500 ships. American yards were producing hundreds of ships monthly by late 1944. The industrial capacity gap was unbridgeable. Germany's entire industrial economy, already strained by fighting the Soviet Union and defending against Allied bombing, couldn't match American production in any category that mattered. The US built 16 large fleet aircraft carriers during the war. Germany built none. The US produced nearly 100,000 tanks. Germany produced about 24,000. The US produced 300,000 aircraft. Germany produced about 120,000. These disparities reflected fundamental differences in industrial philosophy and capacity. American industry, accustomed to mass production of consumer goods, could pivot to military production and apply the same efficiency principles. German industry, despite sophisticated engineering, never fully embraced mass production methods. German tanks, aircraft, and submarines were individually impressive, but produced in insufficient numbers. The Liberty ship program epitomized the American approach. The ships weren't technologically advanced, they used obsolete engines. Their design dated to 19th century British freighters, but they could be produced in enormous numbers by semi-skilled workers using standardized components. Quantity became its own quality. After the war ended in August 1945, the Liberty ship program faced an abrupt halt. Contracts were cancelled. Ships under construction were scrapped on the ways. Workers who'd built vessels for 4 years suddenly faced unemployment. The massive shipyards, built in months during wartime emergency, became economically unviable in peacetime. Kaiser's empire contracted dramatically. The Richmond shipyards reduced operations, eventually closing entirely. The workforce that had numbered 200,000 during the war shrank to a few thousand by 1946. Many workers returned to pre-war occupations. Women were encouraged, sometimes forced to leave industrial work to make room for returning veterans. African American workers found many of the economic opportunities that had opened during the war, closing again in peacetime. The Liberty ships themselves faced uncertain futures. Designed as emergency vessels expected to last 5 years, many were in remarkably good condition at war's end. The Maritime Commission faced a surplus of over 2,500 ships, for which peacetime demand was unclear. Some were sold to commercial shipping companies, others were placed in reserve fleets, mothballed in harbours and rivers, preserved in case of future emergency. Many Liberty ships served far longer than their designed lifespan. The SS Jeremiah O'Brien, launched in 1943, remained in commercial service until 1946, then was placed in reserve. She was reactivated for the Korean War, served through 1953, then returned to reserve. In 1979, she was acquired by a preservation group and restored to operating condition. Today, she's a museum ship in San Francisco, one of only 2 surviving operational Liberty ships. The Greek merchant marine acquired dozens of Liberty ships after the war, operating them into the 1960s and 70s. Some were substantially modified, lengthened, re-engined, converted to different purposes. The basic hull design proved adaptable and durable. Ships designed to last 5 years were still carrying cargo 30 years later. Henry Kaiser's trajectory after the war reflected both his triumphs and the changing economic landscape. He attempted to enter the automobile industry, partnering with Joseph Fraser to form Kaiser-Fraser Corporation in 1945. They produced about 750,000 cars through the early 1950s, but couldn't compete with established manufacturers. The company eventually failed. Kaiser's steel mill at Fontana thrived, becoming a major producer of steel for West Coast construction. His cement company continued operating. Kaiser Permanente expanded into one of America's largest healthcare organizations, eventually serving millions of members. Kaiser himself remained active in business into his 80s, developing real estate in Hawaii and California. He died on August 24, 1967, in Honolulu at age 85. Obituaries praised his wartime contributions, but many younger Americans had no idea who he was. Unlike military commanders whose names remained famous, the industrialists who'd enabled victory faded from public memory. Kaiser received no monuments, no ships named in his honor during his lifetime. His legacy was scattered across industries he'd transformed rather than concentrated in obvious memorials. The lessons of the Liberty Ship program influenced post-war shipbuilding worldwide. The prefabrication methods Kaiser pioneered became standard practice. Modern shipyards build major sections in enclosed facilities, then assemble them on the ways exactly the process Kaiser developed. Welding replaced riveting completely in commercial shipbuilding. The principle of standardized components manufactured by multiple suppliers became fundamental to complex manufacturing. The military lessons were equally significant. The Pentagon's planning for future conflicts incorporated industrial capacity as a strategic variable. The National Defense Reserve Fleet maintained ships in mothballs, ready for reactivation in emergency. The concept of surge production, rapidly expanding output during wartime, became central to defense planning. Industries were identified as strategically important and received government support to maintain capacity. The Cold War between the United States and Soviet Union became partly a competition in industrial capacity. Both sides understood that a major war would be won by the nation that could outproduce its opponent. The nuclear standoff prevented direct military confrontation, but the industrial competition continued. The Soviet Union matched and sometimes exceeded American production in categories like tanks and artillery, but in overall industrial capacity, complexity, and efficiency, American industry maintained advantages that traced directly to lessons learned during World War II. The Liberty Ship program demonstrated that engineering problems yield to systematic analysis and organizational will. When Kaiser first proposed building cargo ships using assembly line methods, traditional shipbuilders declared it impossible. They were wrong not because their technical understanding was flawed, they correctly identified the complexity of ship construction, but because they couldn't imagine organizing that complexity differently. Kaiser succeeded by refusing to accept that established methods were the only methods. He looked at ship construction as an outsider, saw parallels with dam and road construction, and applied principles from one domain to another. This cross-domain thinking, this willingness to ignore industry conventions, proved more valuable than deep technical expertise. The principle applies beyond shipbuilding. Complex problems often remain unsolved, not because solutions don't exist, but because experts can't imagine approaches that violate established practices. Outsiders, unencumbered by conventional wisdom, sometimes see solutions that insiders miss. Kaiser never became a traditional shipbuilder. He remained a construction engineer applying construction methods to maritime problems. That perspective was his advantage. The workforce transformation proved that complex tasks can be decomposed into learnable components. Traditional shipbuilders insisted that building ships required years of apprenticeship and comprehensive understanding of the craft. Kaiser proved that if you divided ship construction into specific operations, each operation could be taught in weeks. The workers never understood complete ship construction. They understood their specific tasks. But when thousands of specialized workers performed their tasks in coordinated sequence, ships resulted. This division of labor principle wasn't new. Adam Smith had articulated it in 1776, but applying it to shipbuilding at such scale was revolutionary. Modern manufacturing relies completely on this principle. Automobile assembly, aircraft construction, electronics manufacturing all depend on workers performing specialized operations without understanding the complete product. The healthcare model Kaiser developed demonstrated that systematic investment in worker welfare produces economic returns. The Permanente health plan wasn't altruism, it was business calculation. Healthy workers were more productive. Early medical intervention prevented minor issues from becoming serious. The modest upfront cost per worker was offset by reduced absenteeism and higher productivity. Modern corporations accept this principle as obvious, offering health insurance and wellness programs to employees. But in the 1940s, it was revolutionary. Most employers viewed worker health as the worker's responsibility. Kaiser proved that employer investment in healthcare benefited both workers and employers, a genuine win-win that seemed impossible under traditional thinking. The strategic lesson about production as a weapon reshaped modern warfare. Military planners now calculate industrial capacity as carefully as firepower. Wars between major powers become contests of production. The side that can outproduce its opponent in weapons, ammunition, fuel, and logistics eventually prevails, regardless of tactical brilliance. The Liberty Ship program provided the case study that proved this principle. The irony at the heart of this story deserves emphasis. Germany's submarine campaign nearly succeeded in strangling Britain during 1942. The U-boats came terrifyingly close to cutting the Atlantic lifeline that kept Britain in the war. If Germany had sustained that campaign's effectiveness for another year, Britain might have been forced to negotiate peace, or at least dramatically reduce its role in the war effort. But Admiral Dönitz and German naval planners fundamentally misunderstood what they were fighting. They thought they were fighting British and American ships. They were actually fighting American industrial capacity. The distinction proved fatal. Ships could be sunk. Industrial capacity, once mobilized, was invulnerable to naval attack. By the time Germany realized its strategic error, probably around May 1943, when U-boat losses became catastrophic, the war was effectively lost. Germany couldn't build U-boats fast enough to replace losses. Germany couldn't sink Allied ships fast enough to prevent supply buildup. Germany couldn't develop technology advanced enough to overcome numerical inferiority. The industrial equation had turned decisively against them. The man who made this inevitable wasn't a military genius or a brilliant naval architect. Henry Kaiser was a construction engineer who'd built dams and roads, who understood logistics and organization, who hired capable people and trusted them to solve problems, who believed that most obstacles were only opportunities disguised as difficulties. His famous quote, "Problems are only opportunities in work clothes," captured his entire philosophy. When traditional shipbuilders said cargo ships required 6 months to construct, Kaiser saw an opportunity to prove them wrong. When steel shortages threatened production, he built a steel mill. When workers needed health care, he established a prepaid medical program. Every obstacle became an engineering problem with an engineering solution. The 4.5-day ship, the SS Robert E. Peary, built in November 1942, was the symbolic pinnacle of Kaiser's achievement. It wasn't the most important ship built. It wasn't representative of normal production. It was a propaganda exercise, a demonstration, a proof of concept. But it captured perfectly what American industrial capacity could achieve when fully mobilized and intelligently organized. That ship represented the answer to Germany's U-boat campaign. Not the specific ship, but what it demonstrated. For every day that Germany's submarines prowled the Atlantic, American shipyards were building replacement vessels faster than the submarines could sink them. The mathematical inevitability was overwhelming. Germany couldn't win a tonnage war against an opponent producing ships in days instead of months. The broader historical significance extends beyond World War II. The Liberty Ship program demonstrated that industrial nations could mobilize civilian industry for military production at scales previously unimaginable. The transformation from peacetime economy to wartime production, accomplished in roughly 2 years, proved that modern industrial capacity was elastic and adaptable. This capability shaped the post-war world. Nations understood that industrial capacity determined national power as much as military strength. The race for industrialization accelerated globally. Countries that couldn't match American production levels sought alliances with the United States or pursued industrial development aggressively. The Cold War competition between capitalism and communism became partly a contest of industrial systems which could produce more efficiently, innovate faster, generate higher living standards while maintaining military parity. The Liberty Ship program validated the American industrial model: mass production, standardization, division of labor, systematic training, investment in worker welfare. These principles produced results that craft-based, artisanal approaches couldn't match. The validation influenced everything from automobile manufacturing to electronics production to modern shipbuilding. Today, when container ships carrying thousands of cargo containers cross oceans efficiently, when global supply chains move products from factories to consumers with remarkable speed, when just-in-time manufacturing reduces inventory costs, all of these practices trace intellectual lineage back to principles proven during the Liberty Ship program. The program's legacy isn't visible in monuments or memorials. Few people today remember the Liberty Ships or recognize Henry Kaiser's name. But the invisible legacy, the proven principle that complex products can be mass-produced using systematic methods, specialized labor, and intelligent organization, shapes modern manufacturing completely. The engineers and workers who built 2,710 Liberty ships in 4 years accomplished something more significant than they understood at the time. They proved that industrial production, properly organized, could be as decisive as any weapon fielded in battle. They demonstrated that American industrial capacity, when challenged, could achieve what experts declared impossible. They showed that ordinary people, systematically trained and intelligently organized, could perform extraordinary work. The ships themselves were ugly ducklings, dreadful-looking objects, workhorses designed for 5 years of hard service before being scrapped. But they carried liberty to Europe and the Pacific, just as Roosevelt promised. They sustained armies fighting tyranny. They kept Britain alive when German submarines nearly starved the island into submission. They proved that free people, working voluntarily in a system that valued their contributions, could outproduce any totalitarian regime. That lesson that free societies with industrial capacity possess advantages no military force can overcome proved more valuable than any individual ship. The Liberty ships and the men and women who built them demonstrated a truth that shapes global politics to this day. Industrial democracies, when threatened, possess resources beyond what any aggressor anticipates. Production capacity, properly mobilized, becomes an unstoppable force. Henry Kaiser, standing on that Richmond shipyard in November 1942, watching the Robert E. Peary slide into San Francisco Bay after 4.5 days of construction, couldn't have known how completely his achievement would validate the American industrial system. He'd solved an immediate problem, replacing ships faster than they could be sunk, but he'd proven something larger. He'd shown that American industry, challenged by existential threat, could accomplish what established expertise insisted was impossible. The 4-day ship wasn't just a publicity stunt or a propaganda exercise. It was a declaration, visible to friends and enemies alike. America's industrial capacity, once mobilized, was an arsenal of democracy that would bury its enemies not in superior tactics or advanced technology, but in an avalanche of production they couldn't possibly match. Admiral Dönitz discovered this truth too late. By the time he understood that his U-boats were fighting American factories rather than just American ships, the war was lost. The Kriegsmarine had been buried under an industrial avalanche of Liberty ships, each one representing 42 days of American labor, each one carrying supplies that sustained the armies liberating Europe. The legacy endures not in museums or monuments, but in the simple demonstration that problems yield to organized intelligence and systematic effort. The impossible becomes merely difficult. The difficult becomes routine. And routine, repeated 2,700 times, becomes victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.